Below, we will discuss two techniques in coding theory, folding and streaming. Codes are maps used to encode messages so that errors caused by transmission through a channel can be corrected and the message can be recovered. Folding is a technique applied to algebraic codes. To illustrate this technique, we will consider the Reed-Solomon code. This code is given by the parameters n, k, and q, such that n is between k and q. N is the block length, k is the dimension, and q specifies a finite field. A field element gamma of order n gives a set of distinct evaluation points. A message m is represented by a vector of field elements. This corresponds to the coefficients of a polynomial of degree at most k minus 1. The message is encoded by evaluating the message polynomial over the evaluation points. The resulting code word is then sent through a channel to another party. Because channels can be noisy, the recipient receives a version of the code word that may contain errors. To recover the original message from a certain number of errors, we can use list decoding. The algorithm consists of two steps, polynomial interpolation and root finding. These produce a list of all polynomials of degree at most k minus 1 that match the coordinates of R for at least t values. We then check each polynomial in the list to find the message. A folded Reed-Solomon code is similar but has an additional folding parameter s. This imposes additional structure on the code word by bundling the n coordinates into blocks of length s, so each block becomes a new coordinate. Because of this structure, one error in an original block of coordinates causes the entire corresponding folded symbol to be wrong. Consider the case where s is equal to 2. If the code word has an error pattern where half of the coordinates are wrong, then the folded version can have between half of its coordinates wrong, or even all coordinates wrong. When producing the list of candidate polynomials, the algorithm must consider the possible error patterns the channel could have chosen. Because multiple error patterns correspond to a single folded error pattern, the algorithm needs to consider fewer candidate polynomials, which reduces the list size. In this way, the algorithm exploits the structure to list decode more efficiently. With additional modifications in the interpolation step, it can also correct for more errors.
Alex and Bob are siblings and they live together. They both love to play FIFA online, where they compete with other players across the globe. However, Alex and Bob use different internet services, having a similar ground network. To understand why Bob is sad, let's compare ARC and FEC techniques. In the case of erasures, ARC results in a 3-way delay. This ARC is not suitable for playing FIFA online across continents because the additional round-trip delay can significantly exceed latency requirements for long-distance communication. FEC schemes, on the other hand, increase the correlation among the transmitted symbols by adding redundant information. Thus, FEC is more suitable than ARC for low latency communication. Streaming codes are packet level FEC codes. At each time slot t, a message packet of k symbols is encoded into a coded packet of length n. Consider an infinite stream of such coded packets. The packets are transmitted across the channel, which introduces packet erasures. The message packet at time t must be decoded by time t plus tau at the destination. In each window of length w, the channel is permitted to introduce either a random erasures or a burst of b packets. Consider this example where a equals 2 and b equals 3. The window length equals 4 packets. In the first window, 2 random erasures occur, and in the second window, a burst of 3 packets occurs. Each packet is subject to the decoding delay constraint of 3 future packets. For example, message packet U4 must be decoded by time t equals 7. Without loss of generality, we can set W to be tau plus 1. The capacity C of a sliding window channel model is completely characterized in terms of the parameters A, B, and tau. Let's look at an optimal rate construction for the case when A equals 4, B equals 6, and tau equals 9 using simple streaming codes. Simple streaming codes are based on staggered diagonal embedding approach. Each coded packet is of length 8 and contains 4 message symbols. The remaining 4 symbols are parity symbols. The parity symbols are designed such that this collection of symbols forms an 8,4 MDS code. Let's look at a staggered diagonal embedding of a code word in the 8,4 MDS code. Each column indicates a packet. Thus, a burst of 6 packets leads to the loss of 4 coded symbols. This SDA approach reduces a burst of 6 erasures to a burst of length 4 and converts A equals 4, B equals 6, tau equals 9 to A equals 4, B equals 4, tau equals 9 sliding window channel for which 8,4 MDS code such as Reed-Solomon code is an optimal rate code. Thank you.